Before, we start with a RAG pipeline. Let's start with having an understanding of a concept called embedding. In the world of AI, embeddings are a fundamental concept. They're numerical representations that capture the meaning of words, phrases, or even entire texts. Imagine these three sentences. 1. The cat chases the mouse. 2. The kitten hunts rodents. 3. I like ham sandwiches. A human can easily see that sentences 1 and 2 are similar, while sentence 3 is completely different. But how can a computer understand this? If we plot the previous phrases on a graph, it might look like this. Embeddings compress text into a multidimensional space where similar words or phrases are grouped together. So, sentences 1 and 2 might be closer together on this map, while sentence 3 would be far away. OpenAI's text embedding model uses 1536 dimensions to represent the complexity of language. This allows computers to understand subtle nuances in meaning. RAG, Retrieval Augmented Generation, is a two-part AI technique that involves indexing data into a vector database and searching the database to retrieve relevant information. Part 1. Indexing the data. The first part of creating a RAG system is to create a knowledge base by load, chunk, and index the data. Step 1. Get the data. Choose a data source for your RAG system. The data can come from anywhere, a document repository, database, or API. Step 2. Chunk the data. Large language models have a limited context window and can't process entire datasets at once. Chunking helps LLMs understand the context of each piece of information, which improves the accuracy of their responses. Step 3. Embedding. Once the text is chunked, the next step is to convert those chunks into numerical vectors, embeddings, that represent their meaning. The quality of these embeddings determines how well relevant chunks can be retrieved for a given query. Part 2. Searching the database to retrieve relevant information. Step 4. User query. A user query is the input that triggers the process of finding relevant information and generating a response. Step 5. Embed the user query. You often embed the user query using the same embedding model as your chunks and search for relevant information. Step 6. Search. Relevant source information. The goal here is to find content that matches or relates to the query. This search is powered by algorithms that can parse the semantic meaning of the user's request, ensuring that the retrieval is as relevant as possible. Step 7. Retrieve relevant information for added context. Following the search, the system retrieves the most relevant documents or pieces of information identified during the initial search. This step is vital as it provides the raw material that will feed into the generation phase. Step 8. Augment the prompt with added context. With the relevant data retrieved, the RAG system augments the original prompt with this new information. This enriched prompt now contains additional context that enhances the understanding of the user's request. Step 9. Query the LLM with the augmented input. At this stage, the augmented prompt is fed into a large language model. Step 10. Deliver improved response to the user. Finally, the generated response is polished and delivered back to the user. This output aims to be more accurate, informative, and contextually relevant than what could be produced by a simple generative model without the augmented input. Let's walk through the Python implementation of this RAG workflow. Prerequisite. To chat with your private Google documents, perform the following steps to authorize access to the Google document. Create a service account by following the steps mentioned at the provided link. Please ensure that you enable Google Docs API if you want to read from Google Documents. The Google document that you want to access should be shared with the service account. Setup. This is necessary for setting up the necessary Python environment. Install required libraries to run code that depends on these libraries. Sentence transformers. This package is used for working with text data, specifically for generating sentence embeddings, numerical representations of sentences. Step 1. Get the data. There are two options. Choose option 1 if you want to interact with your documents stored in Google Drive. If you are choosing this option, then ensure that you have completed the prerequisite criteria. Choose option 2 if you want to interact with the locally specified data source or don't want to go through the Google Drive authentication process required for option 1. Option 1. When you are executing the code for first time, Colab will prompt you to authorize to access your Google Drive. Follow the instructions to complete the authorization. This code is designed to fetch and print the text content of a Google Doc. It iterates through the structure of the document's content, specifically looking for paragraphs and text runs within them. It appends the text from each text run to the doc variable, effectively building a string containing the entire text of the document. Replace the path of the credentials file location with your own file path. Also, replace the document ID with the ID of your own Google document that you want to interact with. Option 2 is simply specifying the entire data source as a string in a variable. The content is a small story involving 4 characters. Step 2. Chunk the data. This line of code takes the entire text content from the Google Doc, stored in doc variable, and breaks it up into separate paragraphs whenever it finds 2 new line characters in a row. The resulting paragraphs are then stored as a list in the paragraphs variable. Step 3. Load a pre-trained embedding model. Responsible for importing the necessary tools and loading a pre-trained sentence embedding model. This model is used to generate numerical representations of sentences, which can be used for tasks like semantic similarity comparison or text classification. Step 4. User query. The query here is a question to identify the character name that revealed the secret map to Alara. Step 5. Embed the user query. Imagine you want to compare the meaning of 2 sentences. This code takes the user's query, a sentence, and transforms it into a special numerical code, embedding, that captures its meaning. This code is then stored in query embed. The normalize embeddings flag makes sure this numerical code is in a standard format, which helps in comparing it to other codes representing different sentences. Overall, this line is crucial for converting the user's text query into a format that can be used for further processing and comparison with the document's content. Step 6. Search relevant source. Information. This calculates the similarity between the user's query and each chunk of the document by performing a dot product between their respective embeddings. The higher the dot product, the more similar the query and the document chunk are considered to be. The resulting similarities variable will hold an array of similarity scores, one for each chunk of the document. Imagine you have a list of scores for different documents and you want to find the top 3 documents with the highest scores. This line of code does exactly that. It sorts the scores, picks the top 3, and gives you the positions, indices, of those documents in the original list. The top 3 IDEX variable then holds these positions, allowing you to easily access the most relevant document chunks. Step 7. Retrieve relevant content. This code takes the most similar document chunks, formats them for readability, prints them to the output, and stores them in a single string variable called context for potential later use. Step 8. Augment input for the LLM. This code is constructing a structured input for an LLM, providing it with the context and question necessary to generate a relevant response. It's like giving a detailed briefing to someone before asking them a question, ensuring they have all the information they need. Step 9. Query the LLM with the augmented input. Before executing this code, ensure that OpenAI's secret key is added to the Colab notebook. This code snippet prepares the environment to make calls to the OpenAI API by importing the necessary library OpenAI and attempting to retrieve the API key securely from the user's Colab data. This setup enables the user to interact with OpenAI's language models and leverage their capabilities in their code. This also sends your carefully constructed prompt, containing the context and your question, to the GPT-4 model on OpenAI's servers. The model processes the information and generates a response. This response is then stored in the response variable for you to use in your program. It's like sending a text message to a very smart AI assistant and waiting for their reply. Step 10. Generate a response to the user. This line of code takes the response from the LLM, navigates through its structure to find the generated answer, and then prints it out for you to read. A link to the accompanying Colab notebook will be provided in the YouTube video description for those interested in replicating the experiment. RAG can be implemented through a number of different frameworks like LangChain or Llama Index for advanced use cases. RAG framework leverages task-specific external knowledge to improve the performance of applications powered by generative models. Now you know how retrieval augmented generation, RAG, works and how to build a functional RAG pipeline. Hope this video was helpful. Thanks for watching.